Of course, you need to create a new workspace. Uh, then after you have created a new workspace, you need to download the transistor file in Canvas like that. So and in this workspace page, you need to first click on Design Kits and choose Unzip Design Kit and find the file you have downloaded just now, and and choose a folder to save the files. It could be saved in the same folder as your design files. So here. So after unzip, you need to choose yes to add the design kit. Then we need to create a new schematic, and the name can be just be the name of the transistor. Uh, if the parts window is not shown, you can right click on a blank space to enable it. And now we need to search the transistor we have just loaded. Not this one. Yes, then you can place the transistor we have just loaded to the software. The first step, we need to create a symbol of this transistor. So we need to place 3 pins. You can place pins like that and connect it with wire. After this, first save this file and go to Window, Symbol, and create a symbol. Let all these settings in default, and you can see that a symbol is created here. Then we need to adjust the position of the pins of this symbol, so we can just drag. You can just drag and change the position of pins like that. After this, click on save, and now we go back to the workspace. You can find that a symbol is created. As we have talked before, so the first step of designing an amplifier is to check the stability performance of the transistor. So we need to create a new schematic and name as BIOS circuit. And we can place the symbol we have just created here, and we need to add some basic components. I have given the working condition of this transistor. So the drain source voltage is 2 watts, and the drain source current is 10 milliampere. So here I will directly give the BIOS circuit to make this transistor working. So you can also find the circuit design in the manual. So it is so the BIOS circuit is constructed like that. After placing these components, we can start the simulation. And to show the current and voltage at these nodes, you can go to the simulate and DC annotation and choose annotate voltage and annotate pin current. So we can find that the drain source current is 10 milliampere now, and voltage is 2 watts. So the transistor is in the working conditions. Then we can go back to workspace to design a new schematic, and this one is the low noise amplifier. We can copy what we have designed it. The BIOS circuit we have designed it to this schematic, and now we need to test the stability performance of this amplifier. So we need to use some components for to the first is the simulations as parameters component. So we need to place as parameters and two terminals to test its performance. And now, and we also need to block the high frequency circuit and the BIOS circuit, as one is DC and one is a high frequency circuit. So we need to use DC feed and a DC block here. So actually, this can be achieved by inductors and capacitors. So we need to place two inductors between the BIOS circuit and the radio frequency circuit, and we need to place two capacitors between the two terminals to block the DC current. Then we place other components. And we adjust the frequency sweep plan of the S parameter component. The value of the capacitor needs to be larger to block the DC current, and this one is same. Now we can start a simulation. I need you also need to place the stable factor component and the maxi gain component to show the simulation results of the amplifier. Then start simulate, and we can create a rectangular plot to first show the stability of the transistor. So I am showing at the frequency of 4G gigahertz. So at the 4G gigahertz frequency now, the stable factor is 0.6. So it is less than 1, which indicates that the transistor is potentially unstable. So we first need to add a negative feedback circuit to let the transistor in stable state. So it can be achieved by adding two inductors. So go back to the basic component and add the two inductors here as the source pin of the transistor, and then we can check the stability. Now we can see that the stable factor has become larger than 1, so it is stable now. We can also place a maxi gain plot here to see the maximum gain at this frequency. So the game is not very good now. So later we will design the source matching impedance network and the output matching network to improve its performance. Then we go to the second step to design the input impedance matching network. So before we start this part, we need to first define our substrate. So it is similar to the first project we have done. You need to first place the M sub and change the values to the required value of this project. So the permeability is 4.3, and other ungiven values can be left to be unchanged as default. So then we can first show the noise figure and the gain figure of this amplifier. We can first go back to the results plot, and we need to first define the constant gain circles and the noise circles as a which is also the same for the amplifier design in your test or quiz. So there are 3 equations to define the constant gain circle and the noise circle. You can find the equations in the menu, and you need to type into the equations in the ADS here. So this is the first equation. And the second, this is the constant gain circle. Oh, this is the noise circle. Uh, so actually we need to enable the noise calculations here. So double click on the S parameter component and enable the calculate noise, and we need to first make a simulation here. So then the equation will not be show errors. This is the constant gain circle. So after we define the two series of circles, we can choose this button to create a Smith chart. So we need to choose the equations of what we have defined just now. So and place all these circles here. So now we can find that the red series of circles is constant gain circle, and the blue series of circles is the noise circles. And we can place two we can also first place a rectangular plot to show the noise. So the noise is now 0.8, and we need to place two markers at this minimum noise point, which is the smallest circle, and the maximum point, which is at here. Can move the results to this place. So it is obvious that the maximum gain point and the maximum noise point, the minimum noise point is at different positions. So at this point, we need to sacrifice some gain to improve the noise. So we need to we choose to sacrifice some gain. So the gain will be dropped from 12 to 11, and now at this circle we can find a place that these 2 points are at the same place. Now we need to remember the keep track of the impedance of marker 5 now. So which is at this impedance is what we want at the input impedance. So now the input matching network is to transform the matched impedance to this impedance. So to complete the design of input impedance matching network, we need to use a component. You need to find the component in this playlist, and you need to go scroll down and find a tool called Smith chart matching. You can this component you cannot be searched in this software. You need to find the Smith chart matching first to place this component. And first we place the component here. And now we also need to use a design guide function of ADS. So we first choose the amplifier choice and go to the tools and find the Smith chart utility tool, and now we will open this window. So now so this tool can help us to do the impedance matching design. We need to first define the source impedance first. So we can go back to the result here. So now the source impedance can is 1.848, and plus my j multiply 0.792, and we can find that the software automatically help us to find the position the point position in the Smith chart. So after typing these two values, it is suggested that you choose the log source impedance. Wait a minute. There's no instance. Can first we can first have a try if it works. So we first choose an open circuit stop here, and it will change the inductance from the matched source and a transmission line to move its phase. So after we place these two components, we can adjust the two pins here. So we can adjust the position of these two pins to let the end of this trace to go to the center of the circle, like that. Then we can click on build ADS circuit here. Now we can find that it automatically help us to design an input matching network. So now we need to copy these two this transmission line out and replace this component with these two transmission line, and it also need to be careful as the impedance matching network is first the open circuit stop, then the transmission line, and we can adjust the position of these names to avoid we cannot see very clearly. Then we also need to turning the two transmission line as well to as there will be some deviations if we directly use the result of the Smith chart matching function. So now we clicked on simulate. We can find that now the minimum noise point is very close to the matching point, which is also the center of the Smith chart. We can open the turning function and adjust the step to a smaller value and precisely adjust the value to let the print to force on the center of the Smith chart, and click on update schematic. Then actually we have finished the this is the procedures of design input matching network. Then we need to design the output matching network. We first need to see the output S22 value here. So we first place a Smith chart and add S22 to the result, and the trace of on the Smith chart actually is the frequency trace. We can see that moving along this trace, the frequency is changing. So we need to first find the point of 4G gigahertz, which is here, and we need to adjust this point to the center of the Smith chart. Similarly, we need to go back to the sketchmatic and place a Smith chart matching component here, and and uh, and we need to notice that this result, this impedance is what we want to the conjecture of this impedance value is what we want to design as the output impedance. So the output impedance, we need to go. We also need to go to the design guide, the Smith chart utility, and now the source impedance should be this the conjecture of this impedance. So Z is 4.363 and 0.466. And similarly, we choose to lock source impedance. And now we adjust like that. So after it goes to the center of the circle, we clicked on the build ADS circuit. And similarly, it automatically generates an output matching network. So we also need to copy and replace the component with this transmission line. Now we can start simulation as at this point is also very close to the matching point. Then we need to adjust it the length of the transmission line as well. So open the turning tool and change the step to a smaller value. And see that it falls on the center of the Smith chart, and then we clicked on update schematic. Actually, now we have finished the principal design of the no low noise amplifier. Then the next step is to change this ideal component to the transmission line component as required in this project. So the first step is to transfer this ideal transmission line to the real transmission line. So at this point we need to use the line calculation function, and we need to adjust these values to the same as here. So mu no change h 1.6 millimeter mu So no need to change, and the frequency is 4 gigahertz. To adjust the unit here, and now the Z0 is 50 ohm, and the effective phase shift is the value here. So now the first section of the transmission line is 110.1. So we copy the degrees value here. So and clicked on synthesize. The result automatically have calculated. So we go back to the transmission line microstrip and place some two real transmission line component here. So the width of the first section of the transmission line is 3.14, and the length is 12.5, and we replace it. Then for the second part is 40. The things 4.57. The position of the capacitor also need to close to the terminals. It will be better. So we connected these components. And we also need to enable the turning of the two components. If your calculation is not wrong, the result of the first Smith chart will only be slightly influenced. No need to change, no need to adjust the performance now. We continue to replace the output matching network. It is which is the procedure is same. We go back to the close some windows first. We go back to the line calculation. Already running. The third is another one is 114, and click on synthesize. And you can simulate here as if your calculation is correct, the result will only be slightly changed. So we finished the first step replacement. Then we need to replace these inductors to transmission line. So so to replace these two inductors, we need to use a circuit structure like that. So we need also need to place two transmission line, and the width of the transmission line need to be as small as possible to increase its inductance. So like the width to be 0.3 millimeter, and the length actually you can choose your the length can be optimized later. We can set a default value here like 13.6. And we also need to use some capacitors. So maybe there's something wrong with the software. It cannot. Need to set it larger. So maybe. Okay, the capacitor needs to be 12. This figure and we need to. This is not connected. To it here as there's something wrong with the obviously the result will be changed. So it then we will also need to add the two transmission line at the input point and output point to make more space for testing. So we need to place two transmission lines here. The width is we have calculated just now, and the length can be chosen as your own number. Then we connect this transmission line to the input port and output port, and after the capacitors, we also need to use a transmission line to connect it with the circuit. So this segment of transmission line needs to be 2 millimeters long. We connect all these circuits, and at this point, there will be the two wires as connected here. So we need to use a microwave component called T here. So we place a T component here and use this to make the crossing, and following it is also true for this point here. So we place a T component. The width of the T component should be set as the 3 points, like that, and it's also true for this one. Before the transistor, there also needs some microstrip lines to connect it with the circuit, and the width is same as the previous one, and the length it can be optimized. We can choose a random number now, and we connect it to the drain port of the transmission to the transistor, and we also need to transform these two inductors to transmission line. We can just use similarly like this one, and it is also true for the drain port of the transistor. We need to add a transmission line here, and the length of it can be optimized later. At this point, we need to add a T. This this place it also needs a T. Then we need to add a transmission line between the output matching network and the output matching network and the capacitor. Then actually we have replaced all the components we needed, and we can now start the simulation. Of course, the result will be deviated very greatly deviated. We need to optimize the values of the input on the output matching network again. So we need to first enable the turning of these two transmission line of the output and the input matching network. Enable the turning of it. And we first adjust the input matching network. It is similar to as what we have done just now. So this will influence the input matching network, and similarly, we need to first find a point that the M4 will force on the center of the Smith chart. If it is out of the range, we need to adjust. We can it is close. We can make the step smaller. Actually, close to the center is okay. No need to be too precise. And now we have adjusted the input matching network. Then we need to go back to the output matching network. The tier 7 and tier 8 will influence it. We first find a value that lets the M6 draw back to the center of the Smith chart. Oh, they are all too large. It is close. We change the step to smaller. It is close now. So so at this point we can create a rectangular plot to show the final performance of the for the amplifier. We can create a line marker at the 40 gigahertz, and now we can show that the gain is now 15 dB, and the output resistance loss is very good. So actually, this we have finished the entire design of this amplifier, and the layout design of this amplifier is not required. And this optional part you can do if you are interested. So this is the end of the demonstration, and after you finish your design, you need to submit a report. It need to contain the basic concept of the amplifier design and the important procedures of the design, and give the result of the 6 required calculation and make some discussion. So this is the end of the demonstration. You can start your own design now.